we talked about, but 1C from the exam, you had already calculated, so if you have a material like this and you put it into tension, it gets thinner and longer, and if our coordinate system is like this, we had already calculated that sigma xx was equal to like positive 7.0 times 10 to the minus 5, and sigma yy was also something, negative 1.5 times 10 to the minus 5. And since the Poisson's effect has to be the same no matter which direction you're looking, the Poisson's ratio has to be negative 1.5 times 10 to the minus 5 over 7.0 times 10 to the minus 5. And it also has to be negative strain, the way I have it written, that would be the ZZ strain over 7.0 times 10 to the minus 5. So that just tells you that the ZZ strain has to be the same as the YY strain, negative 1.5 times 10 to the minus 5, just because of the way the Poisson's effect works. And so then you can just say negative 1.5 times 10 to the minus 5 is equal to the Z change in length divided by its initial length, 0.008, and then that lets you solve the number. Any other questions about the test? Okay. So number 1 from the homework, someone said?
Yes.
Yeah. Do you have it with you?
I don't have it printed now.
Anybody have?
Which part of number 1 was?
Or these structures?
Yeah.
Okay. So this is one of those ones where half of the people in this class learned it one way and half the class learned it another way. Let's do it both ways? Yeah, let's. Why not? Right? Okay. Let's see. So number 1 from the homework. We have this triangular shape, and all the members are connected by pins. And you have a roller over here, and this is just connected to the ground. And 10,000 newtons acting here. Each member has a cross-sectional area of 0.0025 meters squared. And the Young's modulus is 200 times 10 to the 9th pascals. And nu is 0.3. So what material is that?
Steel.
That's steel, yep. And we want to figure out basically the external loads, and then we want to figure out the stress tensors, and then maximum shears and that kind of stuff that we usually do. This is an equilateral triangle, and each member has a length of 1. So I'm going to number these members 1, 2, 3. And the joints I'll call A, B, C. And I'll put my coordinate system down here. Okay, so I'm going to go through this first the way that I did it in statics, and then after that I'll use the trump. Use the Trump simplification. That's just like Trump. I use the trust simplification. Okay, there's no weights on these. Free body diagram of number 1. So the way we're going to do it is we're going to assume that at any joint the pin is connected to the lowest numbered member at that joint, which means at joint A we're going to lump the pin in with body 1. And so down here at A, body 1 feels a force from 3, so I'll call that F13. And it also feels a force vector from the ground, I'll call that RA. Up at the top, it feels a force vector from 2. And then, since that 10,000 Newton force is applied to the pin, we'll put that on member 1. The cool, sort of confusing thing is, magical thing I should say, that's more accurate, is if you looked at this picture and thought that 10,000 isn't applied to the pin, it's applied to body 2 at the place where the pin is, and you did the problem that way, all your answers would come out the same. Okay, so let's write out this table. Pancake, artist, row, 4, marzipan! I guarantee no pancake artist row for Princeton. I guarantee that.
No, I mean, like, why don't you use the Princeton one?
I don't know. I felt like it was petty. I felt like I was making fun of them, but deep down I was only hurting myself. And it's time to let the healing begin.
What is the Princeton one?
Princeton athletes row for mommy. And it was all feeling grumpy and having my feelings hurt by not getting into Princeton when I was a young 18-year-old boy. I was a normal-aged 18-year-old boy, but a young person. Okay, so first, these forces, F13 and RA, what are the coordinates where those are acting? Yep, negative 0.50.
Why did you choose your ballpoint where you did instead of at A?
The origin. So I haven't chosen an about point yet. But I chose the origin there just because all 3 of these points are really simple that way. This one only has a negative x component, positive x component, positive y component.
But you get to cancel out more things if you put it at A.
Well, yeah, so let's put the about point at A. This is the origin, so you can do those 2 independently. You know what I mean?
Yeah. We're playing catch-up.
It fades quickly, I know. But not after this time. It's going to stick. So I'm going to put the about point at A. And so what that row vector is just the vector going from the about point to whatever point you're at. So subtract those two and you get a row vector of 0. And I don't know if I mentioned this, but I was talking to somebody like on Facebook sent me a picture like, hey, I'm using the pancake table. And, you know, like somebody who graduated in engineering. And he left off the first two columns altogether. I never really thought about it. But if you just think of it as always calculating this row vector as just being the vector from A to the thing you're looking at, then you can sort of skip these two and not really think about it. But okay, so the first force I'm going to use is F13x, F13y. Cross product of rho and F is 0. Then the force RA, that also has a row vector of 0 because it's at the same place. I'm going to skip those two. The force vector is RAX, RAY, and the cross product 0. And now up where the 10,000 and the F12 are, the coordinates of that point in the green coordinate system is 0, positive 0.866. The about point has to stay the same. Subtract P minus A and you get positive 0.5, positive 0.866. First I'll do the force F12x, F12y. And the cross product is 0.5 F12y minus 0.866 F12x. Yep.
Why is it 0.866? Shouldn't it be 0.771?
Equilateral is 60 degrees everywhere. See, that stuff gets rusty too.
Yeah.
And then the next one has the same row vector, 0.5, 0.866. The force vector is 0, negative 10,000. So the cross product is negative 5,000. So Newton's second law says F13x, F13y plus RAX, RAY plus F12x, F12y plus 0, negative 10,000 is equal to zeros. And the moment equation says negative 0.866 F12x plus 0.5 F12y minus 5,000 is equal to 0. So the first three equations of this system say F12x plus F13x plus RAX equals 0. The second one says F12x plus F13y plus RAY equals positive 10,000. And the third one says negative 0.866 f12x plus 0.5 f12y equals 5,000. You could look and see if you can solve this yet. You won't be able to. I usually just go till the end anyways and then just solve the big system of equations. It's just a matter of punching values into a matrix. And now we'll go to body 2. Up at the top, okay, so think about this now. The pin is part of member 1. So member 2 touches the pin, so it touches 1, but it doesn't have any contact directly with that 10,000 Newton force. So all we have here is F21, which is negative F12. And then here, the pin is part of member 2. So we have the force on 2 by 3. Is that the bottom one? Yeah. And the force, the reaction force, RC. Pancake artists, row 4. Marzipan! I say it in that voice now. I think it helps. Okay, so the force negative F12 acts at 0, positive 0.866. I'll put the about point at this joint C, so that's 0.50. Subtract to get the row vector. That's negative 0.5, positive 0.866. The force vector is negative F12x, negative F12y. And the moment, 0.5 F12y plus 0.866 F12x. And then down at C, that's where the about point is, so the row vectors are going to be 0. Those forces are applied at 0.50. The about point is 0.50. Row vector is 0. The force vector, let's do F23 first. And the moment is 0. And then RC also has a row vector of 0. The force is RCX, RCY. What?
Isn't it a roller? Just RC1?
Because it's a roller.
Is that roller?
Oh, that's a roller. You're right. Thank you. Yes, very good. So yeah, that force, the force that's applied to that pin by the ground is just a vertical force because that's a roller. Yeah, thanks. That would have screwed everything up. So I'm going to call this the scalar value RC. So that force vector is 0, positive RC, and it's no moment. So Newton's second law says negative F12x, negative F12y, plus F23x, F23y, plus 0 RC is equal to zeros. And the moment equation says 0.866 f12x plus 0.5 f12y is equal to 0. And so our fourth equation says negative f12x plus f23x equals 0. Our fifth equation says negative f12y plus f23y plus rc equals 0. And our sixth equation says 0.866 f12x plus 0.5 f12y equals 0. We have one more body to deal with. So free body diagram of 3. At the left end, the reaction force from the ground is applied to the pin, which is part of member 1, so it doesn't act here. The only thing that this feels is the force on 3 by 1, which is negative F13. And over here, the reaction force from the ground, that upward reaction force, is applied to the pin, which is part of member 2. So all this feels is the force on 3 by 2, or negative F23. Pancake artist, row 4, marzipan. Okay, so let's put the about point at the right end point, I guess. So first the left end point. The origin is in the middle of this, so the location of that force negative F13 is negative 0.50. The about point is positive 0.50. So the row vector is negative 1, 0. The force vector is negative F13x, negative F13y. Cross product is F13y. And then the force negative F23 is at the point positive 0.50. The about point is 0.50. So the row vector is what it, looking at it, it has to be when the force is at the about point, the row vector has to be 0. Force vector is negative F23x, negative F23y, and 0 moment. So Newton's second law says negative F13x, negative F13y, plus negative F23x, negative F23y is zeros. And the moment equation just says F13y is equal to 0. So equations 7, 8, and 9. 7 says negative F13x minus F23x is equal to 0. Equation 8 says negative F13y minus F23y is equal to 0. And equation 9 says F13y is equal to 0. so now we have this big system of 9 equations and 9 variables. Okay, so these are the 9 equations. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the variables are f12x, f12y, f13x, f13y, f23x, f23y, rax, ray, and rc. I guess there's no reason to go this far and not go a little farther. So, can someone read off the coefficients of these from the, so in equation 1, what do we have?
1 f12x, 1 f13x, 1 rax, constant 0.
Okay,
2, 1 f12y, 1 f13y, 1 ray, constant 10,000.
okay,
Negative 0.866 f12x,
okay,
negative 0.5 f12y,
okay,
constant 5,000.
all right,
Equation 4, negative 1 f12x, 1 23x, constant 0.
okay, wait. 2, 3x is positive 1?
23x, positive 1.
Okay.
Equation 5, negative 1 f12y,
f12y, negative 1, okay,
1 f23y,
okay,
0 constant.
okay,
Equation 6, 0.866 f12x,
okay,
0.5 f12y,
okay,
constant 0. 7, negative 1 f13x,
okay,
negative 1 f23x, constant 0.
okay,
Equation 8, negative 1 f13y, negative 1 f23x,
y, right?
negative f13y is negative 1.
Okay,
Yeah.
and then negative,
f23x. Or is that y?
that must be y.
That must be y.
Okay.
I think that's y.
No, I think you had it wrong in the notes.
Oh, okay.
Oh, we just fixed it. Beautiful.
What equation is that? 8?
8.
No,
Oh,
there's
I-
one further up that I thought you had.
Yeah, I wrote it
Should
down.
have been a lie.
Mm.
I think it was like number 4.
Oh, yeah. Equation 2.
Yeah, but I gave it to you.
You gave it
As a
to me
y.
correct, yes.
Equation 8, negative f13y,
Mm-hmm.
negative f23y,
Yep.
constant 0.
Okay.
Equation 9, f1 f13 is 0.
F13x,
F13y,
Y.
sorry.
and then 0, right. Okay. Has anyone started punching this in yet? Okay, let's get at least 2 people to do this, and then... You don't have anything yet? This is taking longer than I'm used to. But I can't complain because I'm not even doing it. But inside I'm complaining. Okay. Okay, let's put it up here and then
It's called it also.
For F12, I have negative 2886.8.
2086?
2886.
Oh, 2886.8.
And then 5,000.
Okay.
For F13, I have 2886.8 and 0.
Okay.
For F23, I have negative 2886.8 and 0.
Okay.
For RA, I have 0 and 2113.2. 2113.2. And for RC, I have 5,000.
Okay. That RA has to be 5,000, I think. And did you get other, anything else different? Oh, really? Ooh, that would be great. Okay, well, let's go with this for now. So what this says, so now if you plug these back into your free body diagrams, for body 1, at the bottom, it's F13 plus RA. F13 plus RA is the vector 2886.8, 5,000. And up here, it's F12 plus that 10,000 Newton force acting down, so negative 2886.8, negative 5,000. And these are acting in the direction from one force to the other one, so you can, if you look at the directions of these vectors, it says that this is in tension. No, that's not tension, that's compression. With a magnitude of force equal to 2886 squared plus 5,000 squared. What do you get for that? 5773. 5773. Then for body 2, up here all you have is the force on 2 by 1, or negative F12. That's 2886.8, and then what was it? Negative 5,000. And down at the other end, you have the force on 2 by 3 plus RA. So that's negative 2886.8, positive 5,000. And again, that's in compression. And then the last one, F. So this one is just equal to tension of 2886.8. Okay, and then the question also asks you to come up with a stress tensor for points in those members. Let's go through it the other way, get the same answer, and then we'll do the stress tensor thing. Any questions about that? Okay, so if you recognize that this is a truss, or recognizing that each member is a two-force member, then we can just isolate the pins and treat those as particles. So the free body diagram of A there's a force this way of F1, a force this way of F3, and a force vector of RA. Then Newton's second law says F1 times a unit vector in that direction. So that's 0.5 F1, 0.866 F1, plus F3 times a unit vector in that direction. So that's just F3, 0. Plus RAX, RAY is equal to 0. So your first two equations say 0.5 F1 plus F3 plus RAX is equal to 0. And the second equation says 0.866 F1 plus RAY is equal to 0. Then a free body diagram of, what's the top one, B? So at B, we have the downward force of 10,000. We have a force this way of F1 and a force this way of F2. And all of this, the assumption that we're making is that each one of these bodies is pure tension or pure compression, so we know the direction is parallel to this. And so it's either positive in the way we drew it, or it's negative in just the opposite way we drew it. So Newton's second law says 0, negative 10,000, plus negative 0.5 F1, negative 0.866 F1, plus positive 0.5 F2, negative 0.866 F2 is equal to zeros. So equation 3 says negative 0.5 F1 plus 0.5 F2 equals 0. And equation 4 says negative 0.866 F1 minus 0.866 F2 is equal to 10,000. And how many variables do we have? I think we have 5 variables, right? So we got to do one more. We have F1, F2, F3, and then RAX and RAY. So we have to isolate the pin at C. That has the upward reaction force RC, a force this way of F2, and a force this way of F3. So Newton's second law says negative 0.5 F2, positive 0.866 F2, plus negative F3, 0, plus 0 RC. And so equation 5 says negative 0.5 F2 minus F3 is equal to 0. And equation 6 says positive 0.866 F2 plus RC is equal to 0. And now we have 6 variables and 6 equations. Okay, so equation 1, 2, 3, 4, 5, 6, and the variables are F1, F2, F3, RAX, RAY, and RC. Can someone read out the coefficients for equation 1? F1? Okay. Okay, and then 0 constant? Okay, and 0? Okay. 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 1 RC and 0. Okay. Can a couple of people solve that one? If we don't get the same thing, we're doing both of these over again. Not really. But I will cry. Okay. So F1 is minus 5773. Minus 5773. Positive 2886. Mm-hmm. And then 0, and then 5,000, and then 5,000. Yay! So here's what this says. It says member 1 is in, the negative says compression. Member 2 is in compression because of the negative sign, and that's also 5773. 5773. And member 3 is in tension because it's positive 2886. Okay, so we got the same thing both ways. The second way was definitely a bit faster. The first way has some other benefits. You can do whichever one you like. So let's take a 10-minute break and then come back at 2:10, and I'll go through the stress calculation for this.
These guys didn't bust me. I gave you bad information, Professor.
Oh,
No one busted me on it.
idiots.
Damn it,
Okay, so all right, so now, okay, shut up. Class is starting. So now we have the internal loads, and we need to calculate the stress tensors. Since these are just in pure tension compression, we can just divide the tension compression by the cross-sectional area, and that gives you the stress. So this first one, the stress tensor in 1, let's think of all of these with a coordinate system, with like their own coordinate system with the long axis along the x-axis. Okay, so each one of these is going to have its own coordinate system. And if you think of it like that, then the XX stress for member 1 is negative 5773 divided by the cross-sectional area of 0.0025. What do you get if you divide that?
Negative 2.3 times.
Okay. And so then the stress tensor is that, and then zeros. That's the same for member 2. And then for member 3, sigma xx is positive 2886 divided by the cross-sectional area. Oh, that's half of this one, isn't it? So this is going to be positive 1.15 times 10 to the 6 pascals, something like that.
You said 1 and 2 are the same then, sir?
Yes, because they are both in compression with the same. And then who can do the principal stress tensor in their head? This one you should be able to do. Neither of these have any shear stresses, so it's already a principal stress tensor. And so that means that what axis would you rotate these around to get the stress tensor with the maximum shear stress? Y or Z. Yeah, either y or z would give you a stress tensor with maximum shear. And what would that value be for the maximum shear for 1 and 2?
Half the value of half of the.
Yep, half of this, and this one would be half of this one. What?
Is that always true if you got one?
Yeah, if two of them are 0, then it's always just half of the other one, because you're still using that same formula, you know, max minus min divided by 2, but your min is 0. Any questions about that one? Oh, where do we trust the results? And where don't we?
Anywhere but the endpoint.
Yeah, we don't trust them at the endpoint where the loads are applied, about the distance equal to the length of that loaded surface. Everything else is good.
So let's say if this beam was a rectangular
Mhm.
cross-sectional beam, in order to determine how long, like what's the distance from the endpoints, do we do the diagonal of the rectangle?
Yeah, but I think, yeah, do the diagonal.
So the longest one you can get from the cross-section?
Yeah. But again, it's not like a mathematical fact. It's just kind of a rule of thumb. Any other questions about this?
So our max shear on 1 and 2 is going to be the 1.15, and remember 3 is going to be half of the 1.15.
Right.
Okay.
That's right. Any other homework questions? Whose is this? All right, well, let's do it. We're going to do a quiz in 10 minutes or something, but let me talk a little bit more about internal loads. So I don't think I gave a general set of steps for internal loads problems yet. Does that ring a bell at all? I haven't done that, have I? Okay. So here's a general set of steps for internal loads problems. So first, calculate the external loads. External loads on the beam. If the only external loads are at the extreme right end of the beam, you can skip that step, but it never hurts to do it. Second, identify the n points where the subfunctions can change. That tells you how many cuts you're going to need, so it's going to require n minus 1 cuts. So third, n minus 1 times. Isolate a piece of the beam that goes from the left endpoint to somewhere between those boundary points. So if you've identified these points where the subfunctions can change here, 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 and here, so there's 4 of them, you're going to have 3 cuts. And your cuts are going to be, you'll have one like this, one like this, and one like this. For each cut, so number 4, for each cut, draw a free body diagram, including the internal loads at the cut. So, for example, if that's the whole body, this is your cut. You have whatever external loads here, and then the internal loads here. And then last, for each cut, do Newton's second law and rotational Newton's second law to find the function t of x, v of x, m of x, and fancy t of x. Okay, so I'm going to do one more example problem. Any questions about the steps? So let's say we have a beam, and usually you have to calculate the external loads. In this one, I'm giving you all the external loads. So let's say on the left end, there's a force of negative 866, negative 500. And at the midpoint, there's a 1,000 Newton force up. And then at the right end, there is a force of 1,000. This angle must be 30 degrees. And there's also a torque at the end of 500. Well, then I missed something. So there's a torque of 500, and then there must be a torque of 500 somewhere else counteracting that. Okay, so how many places are there where the subfunctions can change? the two endpoints, so 2 is the minimum, 3. The two endpoints and then the third one there, so n equals 3, so there's going to be 2 cuts. Cut 1 is valid for x values between 0, I didn't give a length, but it looks like it's 2 meters long. So this is 1 meter, and this is 1 meter. So cut 1 is valid for x values between 0 and 1. So we have the torque on the left of 500, and we have the force vector on the left of negative 866, negative 500. We haven't gotten to the 1,000 yet, so all we have left are the internal loads, T, V, M, and the torque. So Newton's second law says negative 866, negative 500, plus T0 plus 0 negative V. I'm going to start lumping those together because they always appear like this. I'm just going to start writing that as a vector T negative V is equal to zeros. So T is equal to positive 866, and V is equal to negative 500. And then the moment equation, first we'll do the moment about the z-axis. So our about point is at the left endpoint, so the negative 866, negative 500 doesn't produce a moment. The 500 is about the x-axis, so that doesn't appear here. What does is we have a plus m minus vx equals 0. So m is equal to vx. So m is equal to negative 500x. And then the moment equation about the x-axis, we have positive 500 plus fancy t is equal to 0. So fancy t is equal to negative 500. And then the second cut is valid for any x between 1 and 2. So we always include everything from the left endpoint. Now we've gone past where that upward 1,000 Newton force is acting. And we still have that 500 Newton torque. And then the internal loads. So Newton's second law says negative 866, negative 500, plus 0, positive 1,000, plus t negative v, just lumping those two together, is equal to zeros. So t is equal to 866, and V is equal to positive 500. And now the moment equation about the z-axis. Nothing on the left end produces a moment. The 1,000, what's the moment arm for that 1,000? 1 meter. The force is 1,000. And would that make a clockwise or counterclockwise rotation about the left? Counter, so that's plus. And then we have plus m minus Vx equals 0. So m equals negative 1,000 plus Vx. So negative 1,000 plus 500x. And then the last one is the moment equation about the x-axis. All we have is what we did last time, a positive 500 on the left end, plus fancy t on the right end. So that internal torque is negative 500. And if you plot these out so you can visualize what's happening, here's the tension. That's constant over the whole length. A tension of 866. We know it's tension, not compression, because it's positive. The shear force starts out at negative 500 and then jumps to positive 500. The bending moment starts at 0, reaches a absolute value maximum at 1 meter, and then goes back the other way, so it's like that triangular shape, and this value is negative 500 Newton meters. And then the torque about x is just negative 500 the whole way. So if you were looking at this diagram to try to figure out where you're afraid that this thing is going to break, you're most concerned about it, where would you look based on these internal loads? Yeah, right. Everything has everything's pretty much constant. This one jumps, but it jumps over no distance, and the magnitude is the same everywhere. So we would be most concerned about this breaking as you get close to the middle, as that bending moment ramps up higher and higher in absolute value. Somewhere in this range is where we'd be concerned. Maybe we want to bulk up the material there. If it's like a hollow tube, we'd want to thicken it towards the middle, something like that.
What's the last little graph, sir?
This is the torque, fancy T. Okay, that is all.